on the first day in school, I was talking about complexity classes in this talk, showing how what these classes are good for in order to classify problems, and I'm going to illustrate this with the graph isomorphism problem. This is the problem is explained. You have given two graphs, and you have to test whether or not they are isomorphic. This means when there's a projection respecting the adjacency relation. And interestingly, well, this problem has been out for many years, and it's so interesting because it's one of the few problems that is known to be NP, but not believed to be complete in NP. So, and it's not known to be in the class polynomial type either. So it's somewhere in between. Yeah, there may be attempts to classify it better, to find something about the problem that we can say, okay, this problem belongs to this class. I will be also talking about this other problem, GA, is a very related problem, the graph automorphism problem. So here, again, it's about the same thing, a graph being isomorphic with itself, finding a permutation of the vertices that when you apply it, you respect the adjacency. So here, the colors are an isomorphism between these two graphs. And this permutation of the colors, well, there's many permutations, but what is one of them that preserves the adjacency. And probably you have been listening last year, there were very exciting news because Laszlo Babai improved tremendously the best upper bound, the best known upper bound for the problem, which was 2 to the square root of number, n is the number of vertices, times log n, the exponent, to do the polynomial. I mean, what he calls quasi-polynomial. This is a very, so this last quasi-polynomial over P is a very interesting result, making heavy use of group theory. I will not be talking about the result, but you can consider this as complexity class and say, okay, this we already know it's not in P, but it's in this class over P, which is also being improved. So in this talk, I will be talking about all the complexity classes that are maybe not as well known, in showing that the graph isomorphism belongs to all these classes, all these problems. And what is the point in doing that? So there have been other examples in history, for example, for classifying linear programs. People, well, at the beginning, the class did not exist, but if you look at their work, basically Gale Kuhn-Tucker, already in 48, showed that the web was NP, section code P, and much later it was shown to be in P. So it's like when you have a problem and the problem is hard, and you try to classify it, you don't get the best classification at the beginning. Another good example is the prime problem. So to decide if the number is prime or not, in the 70s, it was shown to be in NP, the section called NP, in OMP integral in NP takes really work. Then there's all the complexity classes for P, N to the log n, RP, polynomial time, UP, section code in 92, until we went to the one down. And so I'm thinking that maybe for the isomorphism problem, we get like a similar history that people try to put it more and more classes until finally maybe somebody manages to put it. But it doesn't have to be there, although I believe. So let me start with some basic definitions that we'll be using in this classification attempt. And it's also to do some rotation. So we have to finite groups. A and B, and this notation for equal means that B is a subgroup of A, and we have an element of A. This object here, E5, is, well, the set of permutations that can be written as a permutation, well, not element of B times this 5. This is of course a subset of A because A is because of this operation. It's called a right percent of B. And it's not hard to show that two right percents defined by two different elements are either disjoint or equal. And therefore, the group A is partitioned into different cosets, all of the same size. And these elements that are the ones defined in different cosets are called, I could be right transversal of B. And if we have two graphs, then the set of automorphisms from the graph is a group, and the set of isomorphism is a coset of the automorphism. That means every isomorphism can be written as an automorphism by a mapping between them. And therefore, the number of isomorphisms between two graphs is equal, if they're isomorphic, to the number of automorphisms in each one of them. Okay, so a little more notation. If we have a permutation group, the orbit of I is the set of positions where there's a permutation in the group mapping I to. And this notation means it's the set of permutations mapping I to J. And the pointwise stabilizer, so if we have a subset of 1 to n, by this notation, we have the x here, is the set of permutations that fix every point in big X. So for every element in big X, phi of X is itself. And when we have just one element, I simplify the notation a little bit. The stabilizer of a singleton is with the set of permutations mapping I to S. So when we're talking about graphs, graphs have this property that is very easy to in them to fix elements in the automorphism group. So we have a set of elements, X. We can transform this graph G into another one, by, for example, by putting colors, or if you want colors, little gadgets in this vertices that make them unique, and therefore every automorphism in this new graph have to fix this vertex. Okay, and this is just the notation. If we have, this is the set of in G, fixing all the vertices from 1 to I, and instead of this, I would not denote G, I. Right, and this, what I call pointwise stabilizers, they play a very important role in group theoretic algorithms. We can construct what's called a tower of stabilizers in the following way. First, we start with, these are all groups of automorphisms, different graphs. So we start by fixing all the vertices, like coloring each vertex in a different way, and we have the identity. So there's only one automorphism because every vertex has to be mapped to itself. Then we let one free, and what is it here is just do the identity, And then so on, we start painting some of the vertices black again, until we have all of them black, and we have the automorphism. So it's a way of letting more freedom in the automorphism from completely nothing is able to move to the origin. Okay. Right. So this gives a way to compute the cardinality of the automorphism. So if we have, let's see, this is the subgroup in which point I is fixed, and this is a subgroup of A, and therefore we can find the cosets and partition A this way. There's D different cosets, and this number of cosets is the size of the orbit of I A, so the set of points where I can map to. And in all these cosets, I is mapped to where pi maps it. So I is mapped to 1 of I, because in this part I is fixed, and therefore only the part of the 4. And from what I said before, the sizes of this subgroup are the same. And therefore, the size of A is D times, so we see the size of the orbit here, D times the size of this subgroup. So if we it shows that if we knew the size of the orbit, we can know, we reduce computing the size of A to computing the size of AI. And if we do that for the whole tower of stabilizers, then the size of A is the product of the orbit of I in the different stabilizers or different sets. So if we have a true routine that allows us to compute the orbit or the size of the orbit, we would have the size. And so we have a graph, so some of the vertices are fixed, and if we know to which points we can map I to in this graph, then we could find the size of the orbit. And this is exactly what Malcolm did in the 70s, compute the number of automorphisms in the same way you can compute the number of isomorphisms, exactly by computing the size of the orbit. And the important thing is that this orbit sizes can be computed what we call non-adaptively. But all at the same time, you need to know the size of an orbit of a smaller group in order to compute the next one. You can do it all in parallel. And this is very different to what happens to normal NP-complete sets. So we want to know the number of automorphisms. This is what the other day I was calling like the number of solutions of an NP problem. So automorphisms, NP problem, we want to know how many automorphisms are there. And for an NP-complete problem, you don't know how to do it in any class with polynomial higher. So you have to go to camping class for doing that. And here, not only that, so we're just asking this question, is map being I to J in order to compute the size of the orbit? This is an NP query, but also this queries are done in non-adaptive. So it's a very interesting property that shows that probably this problem already is not NP complete because it behaves very different than other NP complete problems. Okay. slide shows that there is like a canonical way to decompose these subgroups, or a canonical way to factorize each element in the group A in this way, where these phi's right are given by this right transversal. And also, if we have this right transversal, we can test membership in the group and all this all in polynomial. So this is like special kind of generator where the element A is the product of this generator, but it's a canonical way generator. So, showing this classification, then let me recall some of the complexity classes with the counting. So, imagine we have a non-deterministic polynomial time machine, like for an NP problem, and with the notation HCCM accepting the number of accepting paths of an input X on this machine. And yeah, if the machine can make queries to A, then we value A. Opposite to that, the number of rejecting paths, and by gap is the difference between accepting and rejecting. So with this notation, you can define easily several complexity classes. For example, NP is the class of problems for which there is non-deterministic machine, so that in case it is an L, the number of accepting paths is bigger than 0, there is some accepting path and some accepting solution. And if X not an L, then this number is 0. The subclass P, the unique P, is like NP, but in case of acceptance, we have exactly like an ambiguous P, there's exactly one path. And more KP for any K is where you say, okay, what is the number of solutions, what is the number of accepting paths? If it's 0 modulo K, you say the strings of the language, and if it's different than 0, you say it's we will use it for basically with A only for K equals 2, which is the class parity P. So I mentioned that class also on Wednesday. If it is in the language, the number of accepting paths is odd. And well, I think there's something wrong. This should be different than 0. Not different than 1, it's different. So for parity is odd or even. And it's close. So yesterday there were several mentions to this problem. I like it, of tournament graphs. And here's a nice result of classifying an isomorphism problem in this class parity. So we have a tournament graph. This is a click, but with the edges directed. And we see what is the automorphism group in this graph. Well, the identity is always an automorphism, but that's the only automorphism that coincides with its own inverse. No, of course, the inverse of the identity is the identity. But other than that, there's no paired, well, there's no other automorphism that coincides with its inverse. Because if it's not identity, then there should be some point not being mapped to itself in the graph. But since if we coincide with an inverse, we would have that P of P is the same element again. And this implies that either there's an element between I and P of I that is not I, so if there's an edge in this direction, or in the other direction. But when we apply 5, it has to, this changes the direction, because the permutation is the same as the inverse. And then we have that there's an edge in one direction, even only if there's an edge in the other direction, and that cannot be true. So all except for the identity, all the others can be grouped into pairs. The automorphism and the inverse of the automorphism, which is always an automorphism. So you have all these pairs, and then suddenly the identity. So the automorphism group is always odd for a tournament graph. And if we have two tournament graphs, so the number of isomorphisms is either 0 if there are no isomorphisms, no isomorphism, 0 is an even number, or, as I said before, the number of automorphisms, and the number of automorphisms is always odd. So we have here odd or even, so it's a parity argument. So this is not known. Right. The other problem is we will see that there's similar results for general terms. Okay. Now, for functions that this complexity classes, char P is those functions that coincide with the number of accepting paths of a machine or of input, and gap P is those functions that coincide with the difference between accepting and rejecting paths of a machine. Yeah. Well, the difference of two functions. Right? And so here's some classes. This is C equals P. It's a class, it's a counting class that is an exact counting. So if it stays in the language, we have that the difference between accepting and rejecting paths is exactly 0. So you have as many accepting and rejecting. You can exactly say how many paths you're going to have if it's in L, how many solutions. And if it's not in L, then you don't have that number. You have something else. And even stronger, SPT, this is something like if where it was 0 or 1, but yes, the difference between accepting and rejecting paths is either 0 or 1. So here you have 0 or something different than 0. It's 0 or 1. Yeah, this class is also representation. It's like so this is another good result showing that the automorphism problem is in this class. So like we have to make that the number of accepting paths is either, the difference between accepting and rejecting is either 0 or 1. So consider this function. It's a big product, so we have a graph with vertices, it's a big product, so of this difference of these two functions. The set of automorphisms fixing I, and the set of automorphisms mapping I to J. First observe that this function is in this class as gap P because it's a difference of a sharp P function, of the number of accepting paths, so we can the number of automorphisms gives an automorphism, and here also the number of automorphisms mapping I to J gives an automorphism mapping I to J. So there's no deterministic machines have this path, and we will produce also difference between accepting and rejecting. So if the graph has some non-trivial automorphism, non-trivial, the identity is always there, but some other that is non-trivial, the phi mapping I to J, for this I and J, we have said that these two functions are the same. No, the two cardinalities are the same. The number of automorphisms fixing I and the number of automorphisms. This is like automorphism mapping I to itself and the automorphism mapping I to J. This for this cosine properties, these are the same. So for this I and j, which have a big total, but for the correct I and j, these two numbers coincide, so we have here a zero factor, so the whole thing is zero. On the other hand, if there is no non-trivial automorphism, then this second part, for every j different than I, it's always zero. And so we're left with a product of these first parts, but by hypothesis, there's only one automorphism, only the identity. So all these numbers are 1, so we have a product of 1, and this is 1. So we have that this function is 0 or 1 as we wanted to, because different accepting and rejecting paths, and that shows that this product is listed. Again, this doesn't help us to solve the problem in practice. Let's see, dimensional problem. Well, we show that the difference of some function of this function is anyway hard to compute, but shows us that this problem is very different from NP problems. For other NP problems, you cannot just completely control the set of solutions. Right. And right. In order to show that, in order to show that something is an STP, then it is enough to make computation, like a Turing reduction or a computation, with making queries to set an NP, in which the queries are always like making queries to a UP set. So UP sets is actually hard to find. So it's also hard to organize, make an algorithm querying this kind of sets. But you can make an algorithm that queries an NP set, but you can make sure that for the queries you make, the number of accepted paths is 0 or 1. And if you have that, then by some calculations you can show the probability in this class. And in 90s we showed that for isomorphism, this was not completely like in the previous picture with the number of paths 0 or 1, but we could say, okay, the number of paths is either 0 or another value, in fact, exponential now. And maybe I don't know exactly how it goes. It's not really late, but yeah. Well, we managed that we can compute isomorphism by making queries to NP with a set of answers either 0 or this was improved later by where they actually managed this problem. We had 0 and n faculty, they have the bring to 0, 1. So for the isomorphism problem exactly, this result I showed you before for automorphism. So it's classifying this. How it goes. Okay, another example of this classification defined. So Niedermeyer and Fanning, they extended this idea of UP to algorithmic machine, and this was motivated by games within the winning strategies. So if you think about, for example, a meme-like game, if the first player has a winning strategy, but has a unique winning strategy. If he makes, or some games, if he makes the wrong strategy, then the second player has a winning strategy. And this winning strategy is also unique. So this is a unique move on the first player and they win. So whatever the second player makes, there's a unique way for the first player, so it's always unique. And moreover, if the first player makes a wrong move, there's a unique move for the second player. So it's like hierarchy of UAP things. And this is UAP. And they show that in fact is subclass of this SPT as before. So it's even more restricted, although of course what happens in complexity class can be that they are the same. That's the loop. And this other evil proof that what I was saying before, the class problems that can be computed with UP-like queries to not represent an NP, like many also queries that have either 0 or 1 solution, then you prove inclusion in this class UAP. So as a corollary, using the result of R4, we show that, it showed that the isomorphism process is in fact in these other. It's a little more restricted than SP. Right, and there's also been some attempts to, very well known, to already from the 80s, to classify the problem using probabilities in complexity classes. In fact, Papai introduced for that this automorphism games. Automorphism games is like an extension, a probabilistic extension of NP. You have this randomized operator or an NP operator. And so it's like the same way as RP or PDP is a randomized version of P, this is a randomized version of NP. And the standard method for showing that some problem, isomorphism problem is in this class AM, well here's this other wrong, which is different and it should be equal. So we have two structures and we want to prove that they're isomorphic or not. And we define a set in NP as a function so that if they're not isomorphic, the cardinality of the set is twice or bigger than this function. There's a gap between being in the set and not being in the set. And then if you have this set in NP, it's either set in size or twice the size, and by using randomized hashing, you can in fact decide which of the cases you have. And this is the way to prove this thing. And yeah, for the isomorphism problem, this set that is either has certain cardinality or twice the cardinality is exactly this one. You can prove it with your head with the see that it's like this. So you define, given two graphs here one, G1 and G2, you define the set of H. H is a graph, so a graph in vertices that is either isomorphic to G1 or isomorphic to G2. So another way to say that is that you make any labeling of vertex G1 or any labeling of vertex, any labeling of the vertices in G1 or any labeling of the vertices in G2 with the numbers 1 to n. And phi is an automorphism of this graph, so it can be an automorphism of G1 or an automorphism of G2. So, and it's not very hard to see that this cardinality, if the graphs are isomorphic, then for H you have only basically the set of labelings of G1, which are the same thing as the set of labelings of G2. This is factorial. And if they're not isomorphic, then this set of labelings does not coincide with that. And they're isomorphic, and therefore you have twice. And this proves that the problem is in this class AM. And this has been, so this is this AM, as I said, is like a probabilistic version of NP. And this result shows that the complement of isomorphism, non-isomorphism, is in this randomized version of the P. It's like saying it's almost in it. So the problem is almost in NP intersection coordinate. It's like in this randomized version of the P for the complement. And yeah, there have been some attempts to de-randomize this protocol, and under some harmless hypothesis, in fact, A would be NP, and that would show that the problem, the isomorphism problem, is in fact in NP intersection coordinate, which is not common. And this harmless hypothesis already here was probably very hard to prove. This language, there is exponential time, but I know there is a circuit of size smaller than n coincides with that, and that would imply that these two classes are the same. But in fact, for isomorphism, maybe we need a smaller, a weaker hypothesis. Right? Maybe it's a way to show that the problem is in coinpage. We can randomize the whole area class. So maybe we can just randomize the problem itself. So this is an open question. And again, problems with a different kind of problem, the minimum circuit size problem. This is no problem, the one of the original, I would say, although it's not that well known. So we have a Boolean function given to us by a truth table of size 2 to the n, and an s, also part of the input, and we want to know if it has a Boolean circuit of size s. And this problem is known to be in NP. Why? Because basically you can guess the circuit, and right, it cannot be bigger than 2 to the n, so 2 to the n is the size of the input. It's always the size 2 to the n, but maybe than that. And then, because you have the whole truth table, you can, testing the circuit is equivalent to the truth table will take time proportional to the size of the truth table, which is still so it's not to be complete. It's not believed to be it's not to be NP, but not believed to be complete. So there was hard to show that it's complete because it has these consequences. And recently was proved by this part that this problem, in fact, can be Graph Isomorphism can be reduced to that. So, say this is not a complexity class, it's a problem, but it's going to show, okay, this is not believed to be NP complete, and this problem is reducible to it. So, it gives more evidence that the problem is not. Is also not. So, summarizing a little bit the result about upper bound in terms of complexity classes, well, that's the class I mentioned. So GI is known as classes, also in NP, and the NP complete problems are not known to be in any of them. No. So let me now, with this minutes and a half, look at the problem from the other side, from ambiguity. What is it hard for? It's not known to be complete, probably not be complete, but is it maybe hard for what is it hard? We have the inheritance properties of the problem. So that's the lower bound. Yeah, you know, what kind are the other problems reducible to GI? What are the hardest instances for the problem? And this can be used as benchmark for either for complete algorithms or has some application in proof systems. And just to give you a taste of this, consider the undirected reachability. So you have an undirected graph and two marked vertices S and T, and you want to know if there's a path to it. So this is a standard problem, and I'm showing how this can be reduced to isomorphism. And it's not that hard. So basically you make two copies of the graph, and this point that you're trying to reach, you mark. You fix it by giving it a special color. So observe that there is no path from S to T if there is some automorphism between these two graphs. Again, mapping S1 to S2. So if we map S1 to S2, since this boundary has to be fixed, then we will have some edge in here, but there's no edges in here. So if there is an automorphism, mapping S1 to S2, S1 is calculated to D1. So in this question, there's some automorphism mapping S1 to S2. Again, can be reduced to an isomorphism question. So by making another, again, a copy, so these are what we had. See, this is the vertex we're trying to reach. And now, well, you color them in a different way here. One like the same color as this one, and this one is the same color as this one. So these two graphs are isomorphic. Then this graph has to be mapped down here, but on the other hand, this bar has to be mapped up here. And this can only happen if there's no edges in here. This can only happen if they're not reachable. So we are showing non-reachability is reducible to isomorphism. And since this reachability problem is hard for logarithmic space, it shows that okay, all of the space can be reduced to graph isomorphism. And so the question is, can we do better than those? And actually we can. And this is the method of doing that. We try to do multiplication gadgets for group operations, or for other operations, but since the isomorphism problem is so symmetric, you need some kind of operation with satisfaction. So we try to do by multiplication in a group, simulating that by isomorphism. So imagine we have this, we call it like a multiplication gate. We have two elements of the group, and you multiply them, and it comes out the product of them. And we're trying to simulate that by isomorphism. So you can make a graph. Here's the different values that can take this element of the group. Here's the different values of the other element. So we connect element I and j with on the vertex marked ij, and this should give us the product I times j. And this works for abelian groups. So if the group is commutative, you can do exactly this trick. So imagine, this is for addition modulo 2. So you have two values, 0 and each one, 0 and 1. And a 0 would be encoded into an automorphism that maps 0 to 0 and 1 to 1. And a 1 by an automorphism maps 0 to 1 and 1 to 0. When you either you twist here or keep it and here too. And this is translated here in this gadget has this property that you have here 0 or 1 in both of them, and in the output you get 0 plus the sum of both inputs. And then I have to go in detail. It goes in this gadget. Case A is in the Boolean group. This element is encoded by mapping element I into A times I, and then in the level 1, that's what happens. Level 2 multiplication, and the level 3, because the group is abelian, you have actually this, but you can commute and right. If for an element that is can be decomposed in this I and j, is mapped to actually to origin. X, j. And this can be, these gadgets can be, you have like a circuit with these gates, like in addition to the two gates, you can translate that into a graph, and by studying the automorphism group of this graph, actually you're simulating this loop. And this graph actually has appeared in the literature in another context. It's called the CFI graph. If we have, okay, how complex it is to evaluate, like the circuit value problem, but the gates are not and or, like some operation in a group. How hard is that to find the groups? Well, for abelian groups, this has the class called the determinant. So here is an NC2, known to have all this in it. And from this, it follows that graph isomorphism is hard for this determinant class. So we're inside each. What would be very interesting is to see if we could make something like this for non-abelian, because circuits with non-abelian group, for example, permutations over 5 elements, give us all the power of p. That would work. Then this side, I only know how to do for a very special certain kind of circuits, basically trees. And we do have the same thing. And here, before we were representing the elements like I, which meant we want to represent element A, that I being represented by A times I. So here, the way we do it is like each element in the group will be associated with a set of pairs, this n pairs, ij, which should be k. K is the first ij. And, or here should be A, whatever. And so an element A would be encoded in this part as this permutation. We have a left permutation, or a left element, multiplying I, and then a right element. With the property that L times R give us A. Observe that there's many ways to encode, so we're encoding in this part here, or in this part, there's many ways. So once we encode an A, we factor A in two elements, left and right, and we multiply first times left, the element, and then from the other side, right. And, yeah. And here, it shows that we have this property. For every pair of elements, if we, here, this will be the output gate, so it will be here L times T. I mean, that would be the right part. If we use here the same, the inverse of this element in the group, then it actually happens what we want, that you multiply L times R. But only if we use this tree. So for every element, you have this property. And that allows us to reduce tree evaluation over any kind of finite group. So we have in the binary tree with a group element in each leaf, and we want to see, so multiplying it in the normal way, and also consider the order of this group is not commutative. At the end, we get the identity or not. We can reduce that to isomorphism. Fortunately, this problem is not very hard. So, yeah, it shows a little bit how it goes. Because it's an NC1. which isn't a logarithmic space. But this gives us another way to show, different from the one we showed you before, that NC1 is the graph isomorphism is hard for NC1. So it would be very good if we could extend that to not only to trees, but to any circuit, because that would show p-completeness of p-hardness of graph isomorphism, which is a big open question. And this was all actually another way of saying barring characterization of NC1 as multiplication of basically what is barring. So summarizing now, looking from the other perspective, that's class T. Here we have isomorphism not known to be T high, and this is like a picture of classes underneath, one and an L. The determinant of this is reducible to GI. NC2 is not known, and that would be, or maybe even AC1 would be like the next step to try. But it can be, of course, that this product is not hard to be. That is something between, not known to be P, but also not hard to be. That could very well happen. To put both things together, this classification of them are here. Again, this doesn't give better algorithms for the problem. It's not comparable to the result of Popeye. But for us, complexity theorists, help us to understand better some properties of the problem and to show that it's very different from other, for other classes, for this compound unique problem, natural unique problem in the universe. So thank you very much. All right.
You say that for these groups, the multiplication problem, the surface evaluation problem that reduces to GI. So, what about, say, we do that for non-abelian solvable groups? Would that imply something?
Right, that's for, yeah, you can do that, but the thing is that if it's solvable, you are still in debt. I mean, so you don't win anything. You can do it more complicated, you can probably do it, but you don't win anything.
So there is no intermediate step. So you
right.
Non-solvable S5 will give you P, and there's nothing in between.
Right. So you go from there to P, and there's nothing in between.
No questions?
No, there was some announcement. No?
So yeah, so Satya is.
Oh,
So we have brief welcome by the first Dr. Local for the last one actually initiative and invited this here.
Okay, first of all, I want to thank Okay, first of all, I want to thank Anirban and the organizing team for this workshop. It's been very good so far. I just came, but thanks for all the organizational efforts. And I want to thank all the speakers and the participants for coming to this workshop and giving the talks. This is part of a thematic here, as you probably saw, of National Mathematics Initiative. NMI initiative at IISc. So NMI. I want to thank NMI for allowing us or giving us support to organize this thematic year. And this thematic year is on complexity theory and cryptography. And this workshop is the second workshop in this year. There was a cryptography workshop in September at ISI Kolkata, and there are 3 more workshops that will happen as part of this year. You can find about those by going to the website. I was going to show it here, but not able to. NMI. So it's basically the math department website at IISc, and this is and cryptography. Actually, I don't remember what. There's something there. But basically, if you go to NMI website, you should be able to find this as the thematic here. So, as I said, there was a crypto workshop in September, and this is a complexity theory workshop, and there will be a complexity plus crypto, complexity union crypto workshop in Bangalore in January 9 to 13, and there will be an arithmetic complexity workshop in Chennai. Veena Mahajan is organizing that February 10. Sorry, I don't remember the exact dates, but you can find the dates on the website. And there will be a crypto workshop, multi-party computation, secure multi-party computation, and IIT Bombay, early March, organized by Manoj Prabhakaran is here, so you can ask him for details. So there are 3 more workshops, so I welcome you to participate and give talks in these workshops. We might even have a 4th workshop, depending on whether we have money or not. Yeah, so I again, thank NMI at IISc for giving us an opportunity to organize this thematic year, and I thank all of you for giving the talks in these workshops and participating. Thank you.
Thanks, okay. So I'd like to invite Professor Mehrotra to deliver a welcome note on behalf of IIT. Professor Mehrotra is the Dean of Research and Development, also a professor in the Material Science and Engineering Department.
Very good morning to all of you. On behalf of IIT Gandhinagar, our director, and on my personal behalf, I extend a very cordial and warm welcome to all of you to IIT Gandhinagar. And at the outset, let me express our sincere thanks and gratitude to NMI for accepting our proposal to host this school come workshop here at IIT. As I understand, the theme of this school is complexity theory, for which I have no clue except for the fact that perhaps it is used for strategic management and organizational systems, which most of the time are very uncertain, a lot of uncertainties, unpredictable, and with a lot of constraints. And therefore, perhaps you would be discussing about predicting the model the systems which are highly complex and have a lot of uncertainties. I can also see that effort of this kind would require a lot of interdisciplinary approach. People from definitely from computer science, mathematics, and many other disciplines would be, and of course from management and other disciplines who understand more about organizations and managerial strategies. So all these inputs perhaps would be the part of the team. I don't know what is the kind of distribution. But one thing that I would want to say that a theme of this kind is very apt for IIT Gandhinagar, because we claim that we are in real sense, not only on paper, in real sense, ours is an interdisciplinary institute. To the extent that we don't have a department structure, there are not many educational institutions in the country which you would find run without departments. We don't have department buildings, complexes, heads of the departments, department labs, nothing of that kind. All the activities are functional based on functionalities. As you would have already noted, and I'm sure during the next 4 or 5 days when you are around, you would notice certain very specific feature of this institute. Starting with the design of the campus, the design of our hostels, etc., that everything is very consciously designed to result in a lot of interactions. People are compelled to bump into each other and interact. We have tried to avoid silos which are normally created in big institutions which have the conventional department kind of structures. So that I think is uniqueness of this institute. Interactions amongst the faculty, students, and the staff. We don't have a hierarchical system in the institute at all. So I hope that the kind of FBM the institute is going to provide to you would be most apt for a conference of this kind, and I'm sure you would have, all of you would have a very fruitful and enjoyable stay in our campus. I'm sure Anirban, when planning this program, would have given you some time slots to go around, move around, interact with the students and faculty within the campus, so that you have get a better feel about the kind of thing that this institute is offering or is planning to offer. So I once again, on behalf of my director, who is not here, and on my personal behalf and my entire organizational team led by Anirban Gupta, once again welcome you all, and hope that this will be a very successful. Thank you.